So we're asked to prove Demoivre's theorem for integer values of n. And we're going to do this in 3 parts. We're going to, first of all, show this is true for natural numbers. Then we're going to show it's true in the specific case of n being equal to 0, although we could have actually lumped those 2 parts together, but I'm going to do them separately. And then we're going to show that it's true when n is a negative integer. Now, this part is a proof by induction, and before I go any further, I should say that you won't be required to do this proof at any time in the course. So this is here just for your information and the sake of completeness. So let's think about what we're trying to show. We're trying to show that cos theta plus I sine theta, or cis theta, to the power n is the same as cos n theta plus I sine n theta, or if you like, cis n theta. Now, I did say that this first part is a proof by induction. So we're going to look, 1, at showing it for n is a natural number, and this is an induction proof. So the initial case I'm going to take is n equals 1. And if we do that, the left-hand side is just going to be cos theta plus I sine theta. And the right-hand side is also cos theta plus I sine theta. So we can say that this is true for n equals 1. And that's our initial case done. And now we need to go on to the inductive step. So here we're going to assume that cos theta plus I sine theta to the power k is equal to cos k theta plus I sine k theta, and that is true for some natural number k. And then what we're going to do is consider cos theta plus I sine theta to the k being multiplied by cos theta plus I sine theta, and that's going to be cos k theta plus I sine k theta being multiplied by cos theta plus I sine theta. The usual induction trick, of course, is that if this line is true, the next line must be true because all I've done is multiply by the same quantity, the cos theta plus I sine theta. And of course, the left-hand side is cos theta plus I sine theta to the k plus 1, because I've just multiplied cos theta plus I sine theta to the k by cos theta plus I sine theta to the 1. And what we're interested in what happens on the right-hand side. And to do that, of course, what we need to do is expand out. So I'm going to get cos k theta times cos theta. Then I'm going to get, so I've done this expansion first, and then I'm actually going to do that bit next. Now, here I'm going to get an I squared, which is -1. So I'm going to get minus sine k theta sine theta. And that would be the real parts. And then I'm going to have I, and I'll have sine k theta times cos theta, and a plus cos k theta plus sine theta. Now, this you should recognize as being an expansion of cos A plus B, and that is cos A cos B minus sine A sine B. And this one here is an expansion sine A plus B, which is sine A cos B plus cos A sine B. And so the top one is going to be cos of k theta plus theta, which we could write as k plus 1 theta. And the bottom one, in the same way, is sine k plus 1 theta. And that does it. If you think about what we had as our initial statement, what we've done is managed to replace a k plus 1 here and having k plus 1s inside here. And so it works. And all you would need now is your closing sort of proof by induction statement. So that is part 1 done. Now part 2, the specific case of n being equal to 0. So we've got cos theta plus I sine theta to the n being equal to cos n theta plus I sine n theta. And we've got n equal to 0. So the left-hand side obviously just becomes 1. And the right-hand side would become cos 0 plus I sine 0. And you should know that cos 0 is 1 and sine 0 is 0. And therefore that is equal to 1 as well. And so part 2 is done. So now we're going to move on to part 3, where we're going to show that this is true for negative integers. Now, I'm going to start by letting n equal to negative k, where k is a natural number, and therefore n is definitely a negative integer. And we're going to consider the left-hand side of Demoivre's theorem, which says that cos theta plus I sine theta to the n, or it just says that. Well, now that we've made this definition, that is cos theta plus I sine theta to the negative k. And that is 1 over cos theta plus I sine theta. And that is equal to, sorry, that one's to the k, obviously. And that is equal to 1 over cos k theta plus I sine k theta. And that's by 1 that we proved above, that this is true for positive integers. Now, how do we deal with this situation, having our complex number on the bottom? We're going to multiply top and bottom by the conjugate. So I've multiplied the top by cos k theta minus I sine k theta. And then on the bottom, because we're multiplying by a conjugate, we get a difference of perfect squares, and therefore we have cos squared k theta plus sine squared k theta, which of course is 1. So I've just got cos k theta minus I sine k theta. Okay, but we know that the cosine is an even function and the sine is an odd function. So I can say that's cos of negative k theta plus I sine negative k theta, but negative k is equal to n. So that's equal to cos n theta plus I sine n theta. And there we have it, because that's the right-hand side of Demoivre's theorem. Now, it did rely up here on the fact that Demoivre's applies for positive integers, but we'd already proven that by induction. So this does work. And so we've now seen that it works for any integer value.